Good morning, everybody. It's 9 a.m. here in San Diego, so we'll begin today's webinar. Thank you very much for joining us, and thank you for your support of the webinars. Today's webinar is focused on ligand docking in ICM Pro. So we're going to be docking small molecules, fragments. We're going to cover different docking approaches such as covalent docking and template-based methods. This is the second webinar in our series. The first one was 2 weeks ago, which you can view on our YouTube channel, which focused on the 3D ligand editor, which involved showing how to modify ligands and optimize lead compounds in a structure-based way. Today's webinar is on ligand docking, and then in 2 weeks' time, we'll be moving on to the virtual screening options in ICM, such as preparing chemical libraries for virtual screening, how to do virtual screening of chemical libraries against one or more crystal structures, incorporating receptor flexibility in ligand docking and screening. And then we're going to finish with a webinar on ultra-large chemical library screening. So you can screen the giga-sized libraries in ICM, so 5 billion more than that in an efficient way. So if you have any questions during the webinar, please use the Q&A option, not the chat, or you can contact us afterwards at info@molsoft.com. Or the recordings are going to be on our YouTube channel, and you can also request a free trial to activate at some point during the series if you want to try the software if you're not already using ICM. So just to summarize the topics we'll go through, with a small overview of small molecule docking, how to identify ligand binding sites, allosteric sites, and cryptic sites using ICM Pocket Finder. Once you found the site to dock to, how to set up the ligand docking, how to remove a ligand from a crystal structure and redock it and assess how accurately it's docked, how to use restraints and templates to guide the docking if you want to do that. We also have capabilities for fragment-based docking and covalent docking. You can also do peptide docking in ICM, but we're not covering that in this webinar. So just an overview, if you're not familiar with MolSoft, quickly, founded in 1994 by Ruben Abagan, who's a professor at UCSD. Max Totroff is our Chief Technology Officer, and Eugene Rouse is our Principal Developer. Over the years, we've competed in most of the major challenges for protein-protein docking and small molecule docking. And we've had long-term collaborations with Big Pharma on various projects over the years. And more recently, we've been moving into different AI approaches for molecular modeling, as well as docking and screening, and developing methods such as Ridge and GigaScreen for ultra-large library screening, which we'll be discussing in a few webinars' time. So all the features that we will show today are on the ICM Pro software, and it contains options for small molecule docking and cheminformatics. You can read in crystal structure. You can analyze that crystal structure by looking at the density. You can do molecular dynamics in ICM Pro. You can do Monte Carlo simulations. There's a full suite of bioinformatics tools, so you can make sequence alignments and propagate the sequence alignments onto structure, so you can map regions where there is identity or diversity between your crystal structures. The cheminformatics tools, you can calculate properties. You can generate multiple parameter optimization models. You can build combinatorial libraries. You can then analyze the structure-activity relationship of structures and of your data and identify activity cliffs. You can also build QSAR, 2D and 3D QSAR models inside ICM Pro. And then we have the docking and virtual screening, which is what we are covering today. And we have peptide and protein-protein docking as well. So as with the last webinar, we're focusing on the EGFR and its EGFR inhibitors. Last time we were focusing on the first generation, and we noticed that a mutation affects how these bind. So we're going to look a little bit more later at the second generation of EGFR inhibitors, which have increased affinity for mutant targets and more complete inhibition of EGFR signaling. And long-term binding may delay or suppress the development of this gatekeeper mutation. So the EGFR is a tyrosine kinase transmembrane receptor and part of the ERB family with HER2, HER3, and HER4. And it plays a key role in cell cycle progression, differentiation, and cytoskeletal rearrangements. So the common mutations are this gatekeeper mutation, as well as exon 19 deletions and exon 21 insertions, which drive, for example, the non-small cell lung cancer cases with EGFR mutations. An interesting paper is this one, if you want to read more about it. But these are the examples we're going to use. We're going to first go back to our original from a couple of weeks ago, erlotinib, and we will redock this ligand, the first generation ligand first, and then we'll do some covalent docking using the second generation inhibitors. So before you start docking, generally you may already have defined your ligand binding site, which is sometimes the case when you have a co-crystal structure, but there may be occasions where either you're trying to improve that co-crystal ligand and you want to see if there's any cavities, additional cavities that you could reach into, or you may be designing a completely new allosteric inhibitor. So we have a method in ICM called ICM Pocket Finder. It finds allosteric encrypted pockets as well as the orthosteric pocket. The method uses only the crystal structure. There's no knowledge of the prediction. There's no knowledge of the substrate, which is sometimes in other methods they use docking or other tools. But what we do is we have like a probe go along the surface of the protein, and we contour the pockets that we identify. And then the pockets are analyzed, and different properties are assigned to each pocket, such as volume, area, buriedness, hydrophobicity. And Merck used ICM Pocket Finder, and they wrote this paper in 2010, but it's still relevant, and we still use it. It's a way of scoring these pockets according to their druggability. So we're going to start first by looking at our protein structure, the erlotinib EGFR complex. So if you open ICM, we're going to go to PDB search here, and we can type in the PDB code, which is 1M17. And just go and just press the binoculars button here, or you can just press enter. So this opens this crystal structure. You can see we have the terminal window here. I'm just going to close it. Everything you do in the graphical user interface, you can also do on the command line. But for this, we're going to just use the graphical user interface. So you can see we have the protein chain, the A chain here, which you can toggle on and off, the erlotinib inhibitor, and some water molecules. So if we inspect the pocket, we'll see that there's this water molecule here, which actually, if we're going to redock this ligand eventually, we need to keep this water in the pocket because it makes like hydrogen bonds, like a water bridge. Let me just, that's not the best way to show it. So it makes a water bridge with the ligand and the receptor. And we'll see that in a minute once we convert it to an ICM object. And so probably if you want to reproduce the binding pose of erlotinib, which is what we're going to do, we probably need to keep that water, although actually ICM redocks it pretty well without that water there. But we're going to delete the loose waters when we convert. So we need to, this is an X-ray structure. It says XR here, so there's no hydrogens. We need to convert it to a ICM object. So we right-click where it says XR here and choose Convert PDB. So right-click and choose Convert PDB. So we have some options about the waters. I'm going to choose Delete Loose. So this basically removes all the waters that aren't making any hydrogen bonds with the receptor or the ligand. So they're kind of just floating there. They're not making any significant contribution to the ligand pose. So let's choose Delete Loose. We're adding hydrogens, so we need to optimize those hydrogens. There is some ambiguity about asparagines and glutamine residues in the crystal structure from the crystallographer. We're going to optimize the hydrogen bonding network for those, as well as the histidines. Just for clarity, I'm just going to overwrite the crystal structure with the converted ICM object, and I'm going to predict the formal charges in the ligand. It uses our pKa model for the formal charges. Just go OK. So this is converting it. So now you can see here it says ICM. So now it's ready for docking and analysis. So our first step is to first look for binding pockets in this structure. So to do that, to use ICM Pocket Finder, we double click on the A chain, go to Tools, and then 3D Predict. So the Tools menu here, and then 3D Predict, and choose ICM Pocket Finder here. This gives you a box with different options. So it's the input selection is the A chain, the protein chain. The tolerance, so it's sort of set to find drug-like pockets. So these are nice buried pockets. If you want to find more protein-protein interaction sites or flatter sites, you can lower that tolerance to maybe 2.6 or 3.6, and it will identify more open sites. You can get the sequence of the sites. You can display the results. If you check keep compounds, it's not going to find a cavity here because it will keep the compound, the chemical, in the pocket, and so there will be no space for it to find it. So just go OK, and this runs the ICM Pocket Finder. So we get this this table, and it ranks it's found 8 different pockets within this structure. You can see them here. You can check them on and off here. So it nicely finds the ATP. This is a kinase, so EGFR is a kinase, and so we have the N-terminal region here, the hinge coming down here, and the C-terminal. And this is the ATP binding site covered by the P-loop here, and the alpha C coming in. So it's kind of a type 1 kinase inhibitor because everything is nicely in place. The hydrogen bonding, the salt bridges are in place here, and we have this nice pocket. If it was a type 2 inhibitor, you'd probably see this pocket extend beyond here towards the the alpha C region. So we found our binding pocket, but we kind of knew where it was anyway. And it actually ranks the ATP site #1 in terms of the properties. So in terms of volume, hydrophobicity, buriedness, the D-lid. So this is the Merck drug-like score that they developed using ICM. And so the higher this value, the more drug-like the pocket. And the other, so blue is a good prediction, good properties for drug design. So if you're looking for other sites, you can maybe discard some of these pockets as not being targetable because maybe they're a little bit too small. So you could delete those, and you can rank them by the D-lid score here. So if if you have something like a molecular glues project or some protein-protein interaction site project, you can use this to find sites for that. But at the moment, we're only interested really in the ATP site because we're going to try and redock allotinib. So let's just first look at the interactions. So if we right-click on the ligand and say pocket, ligand pocket interactions, we'll see that that the ligand makes one hydrogen bond with the hinge region here. You can see this water bridge between this threonine and the water here. And if we just, the hydrogen bond is, if we lower the energy a little bit, we can see the hydrogen bond with the water here and the ligand that we're going to redock. So when we set up the docking, we're going to keep this water in place. But it's not always the case. You may want to delete all waters and assume that they're going to be displaced upon ligand binding, but it's we're going to keep it in this example. So to dock this ligand, we first need to move the ligand out of the pocket. So we right-click on the ligand and choose option Move from Pocket. So you right-click on AQ here and choose Move from Object. So I'm just going to rename it. So you can see now we have two objects. We have the crystal structure and we have the ligand. So I'm just going to rename this just for clarity, crystal ligand. Okay, so now, so even though when you view it in the graphics, they are together. As far as ICM is concerned, they don't see each other because they're separate objects. Then they're not embedded in each other. So when we dock, there will be a cavity here to dock to. If we left the ligand in, there wouldn't be any space to redock the ligand. So we have the ligand here. So we need to redock it. So we could just use the ligand that we extracted. What I would do is I'll go to the sketch button here. Just zoom in, this one with the pencil. And this opens the molecular editor here. And we can search for allotinib. So just click here. You see that they have the properties of the ligand, some Lipinski rules, and flag some groups. And if there are any toxic or reactive groups, it would flag them as chemical alerts here. And so we're going to place this in a chemical table to dock it from a table. So we go to, there's a button here that we just click, and we will call it the table EGFR inhibitors. Go OK. So that places that ligand here. So now we have all our components for docking. We have the ligand we want to dock. So obviously this could be a very large table of many millions, and we will cover that in a couple of weeks' time, but we're just doing small scale docking at the moment. Or you can dock directly from an SD file, or you can read in Smiles and convert to SD. We have a lot of nib here. So we need to go to the docking menu. We choose New Project, and we give the docking project a name. I'm just going to call it doc EGFR. All your docking project files will be placed in this directory. And so you can always go back and find them. They'll all be saved automatically upon setup. So now it's asking you, what is the receptor you want to dock to? We only have one receptor, but you may have lots, and you could use the drop-down button here to find them. But this is the ICM syntax. So it's basically saying it's the one, the object with the name 1M17. And we need to define the binding site residues. So we could do that in different ways. One way you can just, you can take the lasso button here and just make a selection like that. That's perfectly fine. Or you can go to the docking, go back to our table. And we can say, because we've already run the Pocket Finder, we can say, choose the pocket that is this one, which is the blue one. Sorry, let me go back, new project. And you can say define site around this pocket. And you see that we have the green crosses, which is our selection. So now we have 22 residues selected. Another way would be to double click on the ligand that you have in the pocket here and select it and say define site around selected molecule. Or you can run actually Pocket Finder directly in this window. It'll just give you the same pockets as we did when we were running it from the tools menu. So we want to make the receptor maps. So we just choose here and we go OK. So the first question it asks you is this, you can see this probe. I'm just going to take it out here. This is where the simulation is going to start. By default, it's placed in the center of the pocket. But if you have a very large pocket, you may want to move it to a particular region of the pocket. But very rarely we change it. We just usually leave it in the center. And when we go through the method, you'll see that the docking is stochastic. So it's going to jump to a random site in the pocket anyway, the ligand, immediately after the first step. But it's an option. So you go, and then you see this purple box. The purple box is where the maps will be built for the docking, so the grid potential maps. You can make the box a little bit bigger by just dragging in the corner and moving. And then once you're happy with it, you press go at the bottom here, and it will build the maps. So the docking, to set the docking running, we go to the docking menu, and we're going to dock a lot of it. So there are different options. These are for virtual screening. We're going to do sort of small scale virtual docking, really. So we're going to choose the option dock chemical table. This is our chemical table. So we click on here, and it asks us some questions. What is the table you want to dock? So if you read in an SD file, it would be a table in ICM. And so the table name is EGFR inhibitors, this table, and we just go, and there's an option called dock immediately. If you press OK, it's going to dock it straight away. I'm just going to uncheck that option and go OK. So when you uncheck it, it just takes you, it adds this extra panel to your EGFR inhibitor table. And you can play around with some different parameters. So the thoroughness is the length of the simulation. When we do very high throughput virtual screening, we generally use a thoroughness of 1 for speed, but in a more interactive small scale environment, you can increase the thoroughness to 3. And in other more tougher situations, for example, when you're docking to multiple receptors, which we'll cover in a future webinar, you need to increase this thoroughness more. Number of confirmations. So when it finishes docking, it will report the top 3 conformations, and you can sample double bonds, race mix centers, tautomers, shown here. And then to set the docking dock, you press dock. You just need to, if you've already docked this table, this checkbox will be checked. So you need to uncheck it. But in this case, we haven't started docking yet, so we just go to the dock. Okay. So while it's docking, we'll just go through some slides. So ICM ligand docking uses the bias probability Monte Carlo method with global gradient minimization, which was published by Ruben Abagan and Max Totroff here at Molsoft, one of the original ICM papers. The docking, you see, we have this, the docking is finished already, but we'll go through the slides first. So when the docking finishes, you get this message saying exited normally, and just go OK. You just click OK. But the method is a global energy optimization. So the ligand position and internal torsions are optimized by a stochastic Monte Carlo search in the ICM framework. There's a local gradient minimization. The ligand is continuously flexible, so you don't need to pre-generate conformers when docking. And the receptor, so the receptors here, is represented by pre-calculated grid potentials here in this box. So these represent hydrogen bonding potential, van der Waals potential, hydrophobic potential, and electrostatic potential. And so the ligand's fully flexible. There are other options which we'll talk about in terms of receptor flexibility, but it's another webinar. So once it's docked, you get 2 scores. You get the physics-based score and a neural network score. And the physics-based score is based on this predicted different weights based on these items. So it looks at the van der Waals interactions, the attractive and repulsive forces between atoms. There is an energy term for coulombic interactions between charged atoms modulated by a distance-dependent dielectric. There's hydrogen bonding, donor acceptor desolvation energy. So the desolvation energy is the energetic cost of removing the water molecules from the binding site. It's the hydrophobic free energy gain. And there's also a size correction regarding the number of ligands. So these are all weighted. Each of these terms are weighted, and they're trained on a benchmark. So and there's also a penalty for entropy. So so you need to account for the sort of loss of degrees of freedom upon binding when your ligand binds. So this is the physics-based score. The RTCNN score is our neural network score. It's a new score, and it actually outperforms our physics-based score. RTCNN stands for convolutional neural net, including layers that do topological chemical graph convolutions and 3D radio convolutions. So the RTCNN score differs from the physics-based score in the fact that it doesn't have any molecular mechanics or physical energy terms. It is trained to distinguish native light complexes from decoys based on the geometries of putative complexes from the protein data bank. So all favorable or unfavorable interactions are learned from the training examples. And so, yeah, you're going to see some differences between the RTCNN score and the ICM score. The RTCNN score has a lower penalty for like minor clashes due to induced fit. But with both the physics-based score and the RTCNN score, the lower the score, the better the prediction. As the performance of ICM docking is the last industry-wide docking competition and screening competition was the D3R docking challenges. There were 3 that we competed in, and in all 3, ICM outperformed the other methods in terms of redocking the ligand and virtual screening, ranking and scoring, as well as the prediction of binding energies. So these were for FXR ligands. There was a challenge involving kinases and cathepsin, and the last challenge was with macrocycles. So let's just go back to ICM and see how well the ligand docked. So when the docking's finished, you get that little box we saw while I was showing the slides, and then you have the table here. So we asked for 3 different conformations of the top 3 conformations of the ligand. So they're shown here. We have the score, which is our physics-based score. The RTCNN score is shown here. Let me just zoom in. So this is the score. The lower the score, the better. And the RTCNN score. And these are the individual energy components that contribute to the score. So you could in fact write your own scoring function based on these values if you wanted to change it at all for different purposes, but our scoring function performs very well, both the RTCNN and the physics-based. So if you want to see how well the ligand docks, you can just single click here and it overlays those docking complexes. So the other 2, it finds this one, which overlays very well. We color the docked one a different color, and we can compare. So the main difference is really these tails that come out here into the solvent, where there's not really any interaction. The actual density is very poor as well in that region. So the dot one is the green, and the yellow one is the crystal structure. So you can calculate the RMSD between the 2 by going to, first you select the crystal ligand by double click here. And we have this option called orange selection, this green orange. So it's going to convert the green dots here to orange. This enables us to have two selections in one. So we have the orange selection, and then the ligand that we docked, we just double click, and that has the green. See the green selection, and the crystal structure has the orange. So if we go to the tools button and choose analysis and choose RMSD, then you have the 2 options here in this dialog box. We're going to choose the option chemical because we're comparing chemicals. The first molecule is we'll choose the orange selection, and the second molecule is the green selection. So we're comparing those 2. And you go OK, and that reports the RMSD, which would be significantly better if it wasn't for these tails that are sticking out into the solvent, which could be flexible, and the electron density is not too strong in that region anyway. So that's the RMSD. So we may want to guide the docking, which is sometimes useful. So there's different ways to do that, using either templates or restraints. So you can place a fragment of if you have one or more lead you maybe have one or more crystal structures which has a fragment which you're pretty sure binds in that position. You can guide the docking by atomic property field. So it's going to match, when you dock the ligands, it's going to try and match this point based on 3D pharmacophore. Or you can just choose it to match substructure. Or alternatively, you can say, I want all the ligands that I dock to make one hydrogen bond here, or you can have 2 or 3 defined. And you can also define the substructure which will make the hydrogen bond with the protein. So these are the 3 different ways you can restrain or use templates. Let's do that with this project, this docking project. Uncheck that. So we have our crystal ligand. So maybe we want to guide our docking. So we know that this makes a quinazolin group here makes a hydrogen bond with the hinge, and so we may want to we may want to guide our docking based on this quinazolin substructure. So to do that, we can clone the crystal structure. If you right click on the crystal ligand and choose clone, and that will copy that ligand. We're going to call it template. So now we have the template. We're going to strip this down to the quinazolin group and use that. So to edit our template to what we want, we right click on the ligand and choose edit and choose edit compound. And then we can delete the regions we don't want in our template. This, you select, and when you're happy with the template, you just close the window using the red button here, and it asks you, do you want to submit changes? And go yes. So now you can see we have the just going to get rid of all the hydrogen bonds again, a bit messy. So this is our template. This is so we can guide the docking by the template. So we have different ways that you can either match the substructure or you can match the 3D the atomic property fields. You may want to delete. Be careful with the hydrogens. You don't want to match. You want to have this region being connected. So you have to maybe strip it a little bit more if it was a different substructure. But for this process, we're okay. So you want to be careful how you define your template. But you go to use it. We go to docking, go to template, and so now it asks us which object do you want to use as the template. We need to use the drop down button and find the one we renamed as template. And then we have how do you want to match. So you can actually match by atom name, but generally it's not. You can match by substructure, fuzzy. We'll try and use both substructure and APF. In this example, we use APF, which is atomic property fields, which is our 3D pharmacophore method that we can use for virtual screening as well as overlaying chemicals. So we go OK. So now we can add another ligand to our table here. So if we go to the chemical editor, we can just delete erlotinib, and let's read in another EGFR, gefitinib. And then there's a button here that will append this compound to this table. So you can click on this button here, and we're going to append it to the table called EGFR inhibitors. Chemical name is gefitinib, and go OK. So now this is ready to dock. You see that this is already, alotinib's already docked, but we want to dock gefitinib onto this template, and we're going to use APF. So just for visualization purposes, I'm just going to show you what it looks like. So go to chemistry, consensus, go OK. These are the fields we're going to use to guide the docking to. So acceptor, donor, aromatic region. So to dock it, I'm just going to lower the thoroughness just for speed, and just click on dock, and it will dock gefitinib onto this template. Should be relatively quick. But while it's docking, I'll just show you that the other way to do some restraints. If you go to docking menu, it's finished docking, and so now in this EGFR inhibitors docking results table, we have the alotinib docked, and if we scroll down, we get to the gefitinib, which you see it nicely overlaid on our template here. So it's guiding the docking. So another way to set restraints is to say that we want a hydrogen bond here, or you can say I want this atom to always make a hydrogen bond. We can do that by going to docking, and then choose the option restraints, interaction restraints here. So we select the atom we want to restrain to. So if we wanted to make a hydrogen, if we wanted all our chemicals to make a hydrogen bond here, we need to select that atom, and just click on add hydrogen bond restraint. Yeah, so you should be able to select that atom, and it will list it here. You can also sketch the template. You can sketch a group and say, I always want this one. You can sketch like the quinazolin group or something, and say you always want this group to make a hydrogen bond, and it will be restrained to that position. But you must have some kind of attachment point described. So to make the attachment point, you right click and choose attachment point here. So this is a different way of so you get a list of different restraints that you can use. You just need to select the atom that you want to guide it to. So it's not finding. You should get a table there. So that's how to do different docking and restraints. Fragment docking is more or less the same approach, but for fragment docking, we have a database that is relatively small, and it's been possible to pre-validate the scoring individually for each member of the library. So that allows us to sort of estimate sensitivity and specificity, like true positives and true negative rates at any given score for these fragments. So we have inbuilt into ICM like a library of 120 fragments, but you can screen larger fragment databases, but it won't have the statistics with it. So I've done that. So to screen the fragment database that we have inbuilt, you go to the option Fragment, Scan Probes Fragment, and literally just press OK, and it will scan our local database. If you want to screen your own SD file of fragments, you can go to Setup Batch from SD file, but we'll be covering that in the future webinar. So let me just show you the results from the fragment screen. So when you screen the 120, you'll get ranked by score. You can also rank by p-value, and so we have a so you can see which just scan through this, and it has the docking score as well as the p-value, so you can choose fragments that you like. So these, and they also have the PDBs where fragments have been seen in the PDB, so you can compare your docked fragment with these. You just need to click on here, and it will load all those PDBs all superimposed in the pocket with the fragment. Okay. So moving on to the second generation. So the second generation of EGFR inhibitors, they're all covalent ligands, and they are so in ICM you can dock covalently as well. The docking setup is kind of similar, which I'll show. The only difference is that you need to describe the reaction between the transformation of the receptor side chain and the free ligand. So you have the free ligand, and then you have the product comprising the covalently linked ligand and the receptor side chain. So here we have an example with serine, but in our EGFR structure, there's a cysteine that is targeted in the ATP site. So the input ligands are automatically transformed, and the designated side chain atoms are constrained to the correct position in docking during the simulation. And you can use multiple reactions if you've got different chemistry in the ligands you're trying to dock. We have inbuilt into ICM a number of pre-generated covalent reactions for serines, cysteines. There's over 80 prepared reactions that you can use. But if for example, your particular reaction is not there, you can just edit this accordingly to your chemistry. Or we can add it as, you can let us know, and we can try and add it to this database as well. So that we have reactions for cysteine, serine, histidine, threonines, and RNA as well. So you sketch the reaction in the molecule editor. And we also have a method for identifying reactive cysteines. So this is a random forest model that's generated. And there's a score based on different parameters that are seen as ideal for a reactive cysteine to bind. So for example, how solvent accessible the pocket is, what is the environment around the thiol group of the cysteine, distance to what distance to charged lysines and arginine residues, distance to the protein surface. So it will go through, this method will go through the crystal structure looking for reactive cysteines. So we will do that with a EGFR inhibitor. Let's go to ICM. File new, empty. They get a new ICM session. And we're going to read in the covalent EGFR inhibitor called afatinib. So we're going to read in the PDB. It has PDB code 4G5P. And then you can, if we right click on the ligand and choose pocket, ligand pocket, we can then just have a look at the interactions. And we can see that this is the same orientation. So with the hinge, the P loop, we have the covalent bond here with the cysteine. So we're going to redock this ligand in a covalent approach. We can also see the sequence of this protein. So if we right click on the protein and go to uniprot and construct and say extract, construct, and uniprot, it will generate this alignment here. This is the alignment. We can see that this protein structure we're docking to has this common EGFR mutation, the threonine to the methionine. It's fully linked, so we double click here and it will take you to the region. So you see we have the methionine group. So in the first generation inhibitors, there would be a big clash with this methionine, but these second generation, they kind of avoid that region a little bit and manage to fit into the pocket. So let's try and redock afatinib, the ligand we have bound to this structure. So we go through the process similar way. We need to convert to an ICM object. So right click here and choose convert. So right click here and choose the option convert PDB. Just for speed, I'm going to delete all waters and replace the original as before. Go OK. It's converting the X-ray structure to ICM. Now we need to move the ligand from the pocket. So we right click and choose move from object. It's going to rename it just for clarity. So just going to right click and choose rename. Let's call it crystal ligand. And so we go to docking, new project, and I call it doc covalent. The receptor object is this one. This time I'm going to define the pocket based on the position of the ligand. It's just a quick way of doing it. We could also run the pocket finder. Oh, hold on. First we need to identify the reactive cysteines. So we can go to the tools menu. We check the A chain here, double click, go to tools, analysis, and then choose tools, analysis, 3D predict, reactive cysteine, and go OK. And it will run through the model that we have, and we'll give you a table. So it should be relatively quick. And you will get a table with all the cysteines listed, all the different parameters which we mentioned in that slide, and they're ranked by, and they're flagged if they're reactive. So there are two reactive cysteines. One of them is the one we're going to target, cysteine 9797. So we need to set up the docking. So we go to the docking menu, new project. We're going to dock Covalent. I'm going to use the ligand to define the pocket. So I select the ligand here, go docking, new project, find site around ligand. So we have the green crosses around the pocket we're going to dock to. And we're not going to make maps immediately because we're going to remake them in a minute when we define the covalent site. This is the probe. We just go OK. Go. The purple box is good. So we go. And it's making a map. So we need to first, we can just for your purposes, just to see the reactions, you can read in. If you go to File, Open Examples, there's a file there called Covalent Mechanisms. It's in your ICM distribution. And you can see it has 77 different reactions. And we're interested in the cysteine ones. So we have serines, cysteines, lysines. So you see that it has the one we want. We're going to find a cysteine one, and it's this alpha, beta, and unsaturated carbonyl. So you see that this chemistry, we need to also read in the afatinib ligand. So we're going to read in the ligand. We're going to dock. So I'm going to click on here and choose afatinib and put it into a chemical table again. So we can see that this is the reaction, the Michael acceptor group that's going to be reactive. And this matches this part of the reaction here. So we have the carbonyl, and then when it binds to the cysteine, we define the cysteine. Just zoom in to this reaction. You can see that when you sketch it, you need to define the C alpha, C beta, and the sulfur of the cysteine, and then you have the reacted product. So we're going to use this. I'm going to dock this ligand using this reaction. I'm going to put this in a chemical table. I'm going to call it my table. And then I'm just going to put this into move this one into a separate table just for clarity. So I'll select it, choose right click, choose new, and I call it my reaction. If you want to edit it, you can right click and you can sketch your own one. But now we need to select the cysteine that we're going to dock to. So we select the residue here. You need to make sure it's in your docking project receptor here. And then you go to docking menu, choose covalent, and you could just choose the reactions here. These are the same reactions as in that original table, but we separated it. We separated the one we have, so we can select it here, my reaction, and then we can drag and drop it. So select it, and then choose add to docking project, and it places it here. If you have multiple covalent ligands, you'll get multiple. You can use multiple reactions here, and just go OK. And then we will. It's preparing the maps as before. Okay, so now we're ready to dock. So we can go to the docking menu, choose dock chemical table, choose the one with afatinib is called my table here, go OK. I was going to say uncheck dock immediately. I'm going to just lower the thoroughness just for speed and just go dock, click dock. And when it's docking, you can see that it says one background job here. I can't quite get it yet. So one background job here. This bar will show you the progress. You can also view the docking progress if you go to Windows and choose background jobs, and it will show you so it's finished docking. So you go OK. So we have the docking hit list with the score and the other the RTCNN score here. We can overlay the ligand. It's pretty decently docked. We can color it by, just going to color it green. You can see in the, here you can see that it's actually linked to the cysteine 797. It shows you that it's covalently bound. And we can compare the docked to the crystal structure RMSD. So I'm going to select the docked one, which is this one here. Make it orange selection. Select the crystal ligand, double click. So it's the green. So we have two selections, green and orange, one for the crystal, one for the docked. Then go to Tools, Analysis, RMSD, Chemical, and we'll choose orange selection compared to the green selection. We choose the option kept in place because we don't want it to move them. Just go OK. So the RMSD for this redocked is 0.9 angstroms. Okay, so that's where we end the demonstration. If you have any questions, there's some questions in the Q&A. If you have any questions afterwards, please feel free to email, and I'll try and get back to you by email. You can also contact us if you would like a trial license or anything else. Just feel free to email and with your questions. I'll try and answer some questions now that are on the Q&A